Hello everyone, today we're going to do an example question on calculating the pH of a buffer when you add some acid or base into it. Okay, so for this specific question we have is a buffer, you have a buffer, and then we're adding some base into the solution. Recall how buffer works. Okay, so buffer works that just say in this case we're adding some base. So in order to maintain the pH of this buffer, the weak acid from this buffer is going to neutralize this base you added into this buffer. Okay, and then after neutralize it, and then this the pH of this buffer wouldn't change much. Okay, so now let's look into this specific question what we have. Okay, so the information we have over here is that we have a buffer. Okay, then you have 0.1 moles of HC2H3O2. This is acetic acid. Okay, you have a weak acid. Okay, and then you also have 0.1 moles of sodium acetate. Okay, and then this is a salt. Okay, this salt, the pH, the salt turn when you put into aqueous solution. So you're gonna have sodium ion and acetate ion. Okay, this two, and then sodium ion is a cation of a strong base, so it's pH neutral. And then this acetate ion is a conjugate base of this weak acid, which is acetic acid. Okay, so the conjugate base of it. So now you have a weak acid and its conjugate base. Now we have a buffer. Okay, so this is your buffer, and then of course always this K value is given. The K of the weak acid is gonna be 1.8 times 10 to the power -5. So this is the K value for the acetic acid, HC2H3O2. Okay, one more information given is you're adding, so this solution is 1 liter. Okay, so that's your volume, and then you're adding a 0.01 moles of a strong base into this buffer. Okay, and then you're trying to find the pH of this buffer after you added some strong base. Again, the pH is not going to change much of this buffer. However, let's see exactly how much it changed by doing a calculation. Okay, so you have to realize, since you have a buffer, I'm going to draw a picture. Okay, so you have a beaker. Okay, so this is what you have originally, right? You have a beaker, then you have that 0.1 mole of this weak base, and you have this 0.1 mole of its conjugate as weak acid, and now it has conjugate base. Okay, so I'm just gonna write out the main functioning one for this buffer. So this is your buffer. Okay, so this together give you a buffer. Now you're adding some base. Okay, so look at this strong base you're adding. Okay, so this is less moles of the acid base, the weak acid and conjugate base you have in your beaker. So what's going to happen, as we said, this strong base, little amount of strong base will be neutralized by the acid you have. So over here, what's the acid? The acid is this one, the weak acid. Okay, so the weak acid is going to go ahead and neutralize this. So this reaction will be an acid-base neutralization. Okay, so then let's write out the equation. So equation will be, okay, so you're gonna have your weak acid, HC2H3O2. Okay, so you will have a neutralization reaction with the strong base you're adding. Okay, so now after this, all of this strong base little amount will be neutralized completely. So this will be gone. Okay, so anyway, after this reaction, you're gonna have this. Okay, and water. Okay, so that's your neutralization reaction. Okay, so based on this reaction equation, okay, we're gonna calculate how much acid you need to neutralize this base. Okay, so that's a simple question, right? Because this is 1 to 1 to 1 to 1 ratio. Okay, so every 1 mole of your acetic acid will react 1 mole of that strong base. So that's 1 to 1 to 1 to 1 ratio. Okay, so now I'm going to draw a table. Okay, so this table you have, okay, so this is not S table. it's not exact as table. This table helps you to figure out the stoichiometry. Okay, so we're gonna do we're gonna do a table. Okay, so this table again, we don't care about that. Okay, so you can go moles. So this table we base off moles. So you can start with moles before, moles reacted, moles after. Okay, I'm gonna have another row. Okay, so then will be the new molarity. Okay, the reason for that, when we calculate the pH, we need molarity, we need concentration. The info over here is based off moles. Okay, so now let's start this setup. Okay, so you're gonna have HC2H3O2 NaOH and NaC2H3O2. Again, for this piece, I'm gonna swap to the ion because that's the main functioning one. This is what we care about because that's part of water into part of your buffer. Okay, so originally, okay, so again, this table can set up at any moment. For now, I'm setting up at which moment is that you have your buffer. Okay, so I'm gonna fill out the info. So you have that 0.1. Okay, and then you have this 0.1. This is your buffer. Okay, so this 0.1 of each is from your buffer. Okay, and now you're adding this strong base, which is 0.01 mole. Okay, so as we said, it's gonna have that 1 to 1 to 1 to ratio. So that's the stoichiometry. Okay, so I'm gonna put 1 mole of each. Okay, so that means again, I already explained. Okay, so then now you have 0.01 mole of this sodium hydroxide. You need 0.01 mole of this acetic acid to neutralize it. Okay, so you're gonna this strong base will be all gone, right? Okay, so it's gonna be negative 0.01. Okay, because this will be none of this left. Okay, and then you're gonna use 0.01 mole to neutralize it. Okay, and then after this, the product, you're gonna make a 0.01 mole more of that acidic ion. Okay, and then after this, of course, this will be the after the neutralization reaction. What we're gonna have? So we'll have 0.09 moles of this weak acid because you use 0.01 to neutralize the strong base you added. Okay, and then this will be 0 because this is be all gone. Okay, and then you made 0.01 more of this conjugate base ion, which is acidic ion in this acid ion in this reaction. So it's gonna be 0.11. Okay, so that's moles. Okay, and then for this question, it's not bad because we give you what? We'll give you just 1 liter. So in order to calculate molarity, you just need to divide it by the liter. In this case, it's still the same value, but however, the unit is gonna change because the unit is gonna be molarity. Because it's 0.09. Again, you divide it by the 1 liter. Is from the question. Okay, this is 0. And this will be 0.110 molarity. Okay, so now at this moment, after your buffer neutralized the base you added, now you have a new buffer. Okay, so you can think about now you have a new buffer. In this new buffer, you don't have that 0.1 moles of the acidic acid and its conjugate base. Now you have how much? Now 0.1 moles of each anymore. Now you have what? 0.09 moles. And after you calculate concentration, now you have a 0.09 molarity of this HC2H3O2. Then you have that 0.110 molarity of this NaC2H3O2. Okay, so now this is your new buffer, and now we want to know the pH of this solution. Okay, as from earlier, we already talked about Henderson-Hasselbalch equation. Now things are easy, right? Because you can just use the equation. The equation itself is like this, right? pH equals to pKa plus log of the base, concentration of base over the concentration of the acid. Okay, and now since we have the K value of your acetic acid, so we just need to calculate pK. As we already talked about, pKa is just very simple. pK will be just the negative log of Ka. Okay, K value is given from the question. It's 1.8 times 10 to the power negative 5. Okay, after you do this calculation, value turns out to be 4.745. Okay, so that's your pK value, and then the base will be, this is conjugate base. We talk about the concentration. Acid is right over here. We already know, and then you just need to use the Heisenberg equation to finish the calculation. So the pH will be 4.745 plus log of the base, which is 0.110 over 0.09. Okay, so this will be 4.745 plus the value of this, and then you do the calculation. This turns out to be, the final answer will be 4.83. Okay, so this is a pH, but we cannot stop here yet. We need to double check. By how? By doing the small approximation. Okay, so the small approximation you're doing by the concentration of the hydrogen amount over the initial concentration of this acid, and then in this case we don't have the concentration of hydrogen amount, but we can calculate. Okay, since we have the pH, so that's a piece of cake. So you can just do the concentration of hydrogen amount will equals to 10 to the power negative pH. So this will be negative 4.83. Value will be 1.47 times 10 to the power negative 5. Okay, and then we're going to do small approximation by using 1.47 times 10 to the power negative 5 dividing by the concentration of this buffer will be 0.09. Okay, and then this is concentration times 100%, and this turns out to be 0.016%, which will be smaller than 5%. So small approximation is valid. Okay, so this is good. It's valid, so you can actually report the pH of your buffer. Okay, so this will be the final answer for this question.